All right, let's dive into a topic that is, no joke, the absolute foundation of good database design, but one that can feel, well, a little complicated. We're talking about database normalization. Trust me, if you work with data, getting this concept is basically a superpower. So let's demystify it together.
So take a look at this. At first glance, this table seems totally fine, right? It's just a simple list of customers and the stuff they bought. But I'm telling you, this structure is a ticking time bomb, just waiting to explode and create total chaos in your database.
You're probably looking at this thinking, come on, I can read it just fine. What's the big deal? Well, let's play this out. Imagine your boss asks for a report on how many people bought a mouse. You can't just count the rows. You literally have to write a query that digs inside the text of each cell. And what if someone typed mice or computer mouse? See? It gets messy, and it gets messy fast.
These messy situations actually have a technical name: anomalies. Think about an update anomaly. What if a product name changes? You've got to hunt it down and replace it everywhere, and you just know you're going to miss one. Or an insertion anomaly. You can't add a cool new product to your system until a customer actually buys it. And the worst one? The deletion anomaly. Imagine a customer returns their only order. If you delete that record, you might accidentally erase the only proof that a certain product ever existed. Yikes.
Okay, thankfully there is a cure for all this chaos. It's called database normalization. The best way to think about it is as a systematic cleanup process. It's a set of rules that helps us organize our data to get rid of these problems, making sure our database is reliable, consistent, and just works.
So this whole cleanup process happens in stages, and these stages are called normal forms. Let's just walk through the big three. That's 1NF, 2NF, and 3NF, and see exactly how they take our messy data and make it clean.
All right, rule number 1, the very first step in our cleanup is the first normal form, or 1NF. And the rule is super simple, but it is absolutely non-negotiable. Every single cell in your table has to hold one and only one value. We call this being atomic. No lists, no comma-separated stuff, just one single piece of information per box. So if we look back at our original problem table, you can spot the issue right away, can't you? That purchased products column is a classic textbook 1F violation. It's stuffing multiple different items into a single cell, and that's exactly what we have to fix.
And the solution? It's all about breaking up that messy list. To get our table into 1NF, we give each product its own dedicated row. And just like that, our data is now atomic. It's clean, it's organized, and it's suddenly so much easier to work with.
Okay, now that our data is in 1NF, we can level up to the next step, second normal form, or 2NF. The rule here gets a little more specific. It says that every piece of information in a row has to depend on the entire unique ID for that row, not just a piece of it. This is all about hunting down and eliminating something called partial dependency. Check out this example. To know exactly which row we're talking about, we need both the order ID and the customer ID. That's our full key. But look at the customer name. Does John Doe's name depend on which order it is? No, of course not. It only depends on his customer ID. Because his name is repeated for every single order he makes, we're wasting space and creating redundancy. That's a 2NF violation. And the fix here is just so elegant. We split the table. We create a brand new customers table where each customer's name is stored exactly once. The orders table just needs the customer ID to know who it belongs to. No more repeated names, and boom, our data is now in 2NF. Let's take it one level deeper. Third normal form, or 3NF. This rule is all about hunting down something called transitive dependencies. Now, the easiest way to think about this is no piece of info should be determined by another piece of info that isn't the main key. We're basically cutting out the middleman.
In this table, the main key is the order ID. But look at this supplier. Does the supplier HP depend on the order number? Not really. The supplier depends on the product being sold. So the order ID determines the product, and the product determines the supplier. That indirect relationship is a classic transitive dependency.
So you probably know the drill by now, right? We split the tables again. We can create a separate table for products and maybe even another for suppliers. And then we link them all together using their IDs. Now every single piece of information depends directly on the primary key of its own table. This is what a clean, logical, and fully normalized 3NF structure looks like.
From most real-world applications, hitting 3NF is the gold standard. You're in great shape. But in some really complex situations, especially with overlapping keys, there's an even stricter form called Boyce-Codd normal form, or BCNF. And this is a classic example of a BCNF problem. You can see here that the instructor is totally determined by the course, right? Math is always taught by Dr. Smith. The issue is, course by itself isn't the unique primary key of this table. BCNF has a strict rule that says every determinant, anything that determines another value, must be a potential primary key. So this structure breaks that rule, and the fix would be, you guessed it, splitting it into two tables.
Okay, we have spent all this time perfectly cleaning, organizing, and separating our data. So now I'm going to tell you why you might sometimes want to intentionally break all those rules and make it a little messy again. This is called denormalization. And that brings us to a really critical question. Is a perfectly normalized database always the best choice? I mean, it's amazing for making sure your data is accurate and consistent. But all of that splitting and joining tables back together can sometimes slow things down, especially when all you need to do is read a bunch of data really fast.
This right here shows the fundamental trade-off. It's a tug of war. Normalization gives you amazing data integrity and lightning-fast updates. But denormalization, it sacrifices a bit of that consistency for absolutely blazing fast query speeds, simply because it doesn't have to do all that work joining tables. It's a classic battle, consistency versus speed.
So what does this mean in the real world? Well, for systems where you're reading data way more often than you're writing it, think of things like analytics dashboards or big end-of-quarter reports, denormalization is often the right strategic move. You knowingly accept a little bit of data redundancy in exchange for pure performance.
So, after looking at both sides of the coin, let's wrap this all up with why mastering these rules is still an absolutely essential skill for anyone who touches a database.
Look, normalization isn't just some academic exercise. It's the practical, hands-on discipline that ensures your data is stored efficiently. It prevents those dangerous anomalies we talked about, and ultimately, it creates a system that is trustworthy, scalable, and maintainable. It really is the foundation you build everything else on top of. I absolutely love this way of putting it. At its heart, normalization is just about smart organization. It's like creating a well-structured house for your data, where everything has its own proper place, which makes it super easy to find, to update, and most importantly, to trust. And that's our look at database normalization. We want to leave you with one final thought to chew on. In today's world of NoSQL, big data, and AI, with all their flexible structures, how do these classic rules of organization and integrity still apply? And where are they more critical than ever? Thanks so much for tuning in.